Today we'll begin looking at the intro to vectors. Vectors are part of everyone's common experience. Consider a typical winter weather report that you might hear on the nightly news. The temperature is presently of negative 11 degrees Celsius with a wind from the northwest at 22 kilometers per hour. So in this example here, temperature is expressed as a numerical value, and our wind is expressed as a numerical value and a direction. So therefore, quantities having magnitudes are called scalars, whereas quantities having both the magnitude and direction, so i.e. the wind, is called a vector. So some examples of vector quantities are, we have the force, which the force of gravity has a well-defined magnitude and acts in a specific direction, which is down. The force of gravity is measured when you step on a scale. Force is a vector quantity. Displacement. Displacement, when you walk from point A to point B, you travel a certain distance in a certain direction. Displacement is a vector quantity. Magnetic field. Some magnets are strong, others are weak, all cause a compass needle to swing around and point in a particular direction. A magnetic field is a vector quantity. So a vector is generally expressed as such. So the length of the vector is the magnitude, and the direction of the arrow is the direction of the vector. We will stick to 2D vectors for the first part of this unit. However, we will look at some 3D vectors as we move further on. So let's look at an example here. A student travels to school by bus, first riding 2 kilometers west, then 3 kilometers north, and then further 2 kilometers northwest. Represent these displacements on a vector diagram. So you can go ahead and try that out. We will take it up in class. But just talking about a couple of our notation of vectors here. We have u and v are vectors. Also, u and v are also vectors here. Notice that this u and v here are bold. Okay? So vectors are represented by a letter with an arrow on top, or they can also be denoted using bold letters as such. Also, x, y, a, b are scalars. So scalars are written like normal unknown variables. And then we have the magnitudes of vectors. So the magnitude of a vector is expressed by placing the vector symbol in absolute value brackets. The magnitude of a vector is a positive scalar. And AB is a vector that starts at point A and ends at point B. So its magnitude is the absolute value of AB, where A is your tail and B is your head. So a point-to-point vector is often used when we need to know the start and end of a vector. So I'm hoping by now that you've been able to tackle example 1, but let's look at this. So when the student travels to school by bus, he first rides 2 kilometers west. So just by knowing your north, east, south, and west, their starting position is as such, and it heads west 2 kilometers. So we have our head here, which is our beginning, and then we have an arrow pointing to where our tail is. And then it tells us we go 3 kilometers north. So straight up we go north, and that there is 3 kilometers. And then our last part here is 2 kilometers northwest. We don't know exactly how the vector would be going, if it's going to be further north or further west, but so we just go in our northwest position here at 2 kilometers. So that is how we should draw our displacement on a vector diagram. So now we can discuss when 2 vectors are equal, if and only if. So both things need to hold true if their magnitude and their direction are the same. So recall, if those 2 properties exist, the magnitude and direction, and are exactly the same, then the 2 vectors will be equal. Now 2 vectors are opposite if they have the same magnitude but point in opposite directions. And then when 2 vectors are opposite, such as AB, and this should say DC, sorry. Okay. One is the negative of the other. So AB, okay, the derivative of the vector of AB is equal to the negative vector of DC, okay, as you can see from our diagram right here. And the 2 vectors, okay, are said to be parallel if their directions are either the same or opposite. Okay, so the direction needs to be either the same or opposite to be parallel. So remember, 2 vectors are only going to be equal if both the magnitude and direction are the same. So now we're going to look at an example. So example 2, ABCDEF is a regular hexagon. Remember, regular just means that each side, so AB, BC, CD, DE, EF, and FA are equal. So give examples of vectors which are, the first one, equal to one another. So some examples here, the vector AB is equal to ED, and the vector FB is equal to EC. So you notice here they are parallel to one another and they are the same magnitude. Okay, we have FE be equal to BC. And we also have AF would be equal to CD. Alright, so next one, they're parallel but have different magnitudes. So what are parallel and have different magnitudes? Remember, magnitude refers to the size of the vector. So if we look at AF, you notice here, which is right here, is going to be parallel to BE, and it's also parallel to CD. So we have 2 cases here. So AF, okay, the vector AF is parallel to BE. However, BE is larger in magnitude than AF. And BE is parallel to CD. Alright, now part C here. They're equal in magnitude but opposite in direction. So which ones have the same size but opposite in direction? So now, if we look here at our example, you can see AB, okay, is equal to DE, but they go in opposite directions. So AB, the vector, is equal to negative DE. So they're same size but different directions. As well, AB is equal to negative BA. What about equal in magnitude but not parallel? Okay, so that means the size of them are the same but they're not parallel. So there we could look at AB and BC, for example. Lots of different examples that exist. So when we're talking about the magnitudes, okay, we put them in our absolute values. Okay, so AB is not parallel to BC. However, the magnitudes are the same. So what about ones that are different in both magnitude and direction? So what vectors here are larger? So when we're looking at, for example, say BE, BE is larger than any of our other sides here. Alright, so looking at that, we can say, well, AB, alright, so our AB here compared to our BE. So you notice their magnitudes are different and they're in different directions. So AB is not equal to BE. Okay, so those have different directions, and AF is not equal to EB. And their directions are opposite. So I hope that helps you understand when we're looking at our vectors and understanding when they're equal, when they're not, when they're parallel, or even when their directions are different. Now, also note, you can also use the coordinate system to represent vectors. So we want to consider the vector AB, whose tail is at -2, -3. So that's our ordered pair. So let's graph that, -2, -3. So we have a point right here. We can label that as our A. And whose head is at 2, 1. So we go over 2, up 1. So that's going to be our B. Okay, here we can actually connect these two. Be sure to include the arrow, okay, on the tail of it. So A is our head and B is our tail here. So we want to calculate our magnitude. So when we're calculating our magnitude, this goes back to something that you guys learned back in grade 9 when we're talking about magnitudes. So we take the square root of our x2 minus our x1 squared plus our y2 minus our y1 squared. So we can sub in our values there. So we have 2 minus -2 all squared plus 1 minus -3 all squared, which is equal to 4 squared plus 4 squared, giving us square root of 32. We can reduce that, okay, which is equal to 4 root 2. So that's our magnitude of our vector AB. Part B, we want to determine the coordinates of D on a vector CD. If C, okay, starts at our origin, so this will be C right here, and AB is equal to CD. So when they're equal, they have the same magnitude and direction. So if it has the same magnitude, that means it's the same size. So if we look here and we see that we can get from point A to B, we can look at our slope. So we go up 1, 2, 3, 4 and over 1, 2, 3, 4. So since D is our tail, we know that D is going to be our tail of this one. So C is our head, so we're going to go up 4, 1, 2, 3, 4, and over 4, 1, 2, 3, 4. Okay, so therefore our functions will be the same magnitude and the exact same direction. So connect our C and our D, make sure we label that D as well, and put an arrow on the end signifying that D here is our tail. So therefore D is at point 4, 4. Next we want to determine the coordinates of G on the vector GH. So here G is our head and H is our tail. So we are given H, so H is 4, 3. So let's do this one in a different color so we can see it. Okay, so over 4 up 3. Okay, so this one here is H. And now we need to find, well, where is G? So we have to go backwards in this case. So instead of going up, we're going to go down 4. So 1, 2, 3, 4. And we're going to go left 4. So 1, 2, 3, 4. So you notice that G here lands right on AB. So we can connect G and H. Make sure we have our arrows. So when this happens, all right, AB is said to be, and GH, they are said to be collinear to one another because they actually share in the same direction and they're right on top of one another. So G here is at the point 0, -1. So that is our lesson for today.